Hi everyone, good afternoon. Today I'm going to present our recent work with my advisor Tachpon Saranurak, maximal cage connected subgraphs via local random contraction. So I'm going to explain each and every term soon. The outline of the talk, I start with introduction. I explain what is the problem and then explain a folklore algorithm. And then I give a brief overview of the previous work that is done and put our result in the context of the previous work. And then I move on to the key techniques involved in this algorithm, the main framework that the algorithm generally uses, and then the local subroutine, which is the key technique that gives improvement to the algorithm. And I'll go over the local subroutine in detail. And then I'll conclude with open questions and future work. So let's get to the problem. So before we get to the problem, we need to know some definitions. So what is maximal cage connected subgraph? I use it MKS in short. It's a subgraph H of G, which is weighted with weight function W on this edge set, and we can assume it is integral weights without loss of generality, such that the graph H is cage connected. So this is the purple graph in the subgraph of this blue graph G, and this is cage connected. I use lambda to denote the min cut of the graph throughout the talk, and lambda of H is the weighted min cut value of the H, and it is at least K, then it is cage connected. And the maximalness comes, the definition is every supergraph H prime, that is a supergraph of H, has min cut less than K. So that's the maximal. So this is the maximal subgraph, and any supergraph of this has a min cut less than K, and that is what maximal cage connected subgraph. And so an observation, so every maximal cage connected subgraph is an induced subgraph. So although it need not be an induced subgraph, but it will be an induced subgraph because if there is an edge that is not in H, then we can even add that edge, and it will become a supergraph, and so that contradicts maximality. So every maximal cage connected subgraph is actually an induced subgraph on a vertex set. And now that we know that definition, the problem is finding maximal cage connected partition of a graph. So a partition P, which is of vertex set V of graph G, it's basically all these subsets union of these form V, and none of them are having any intersection. And that partition is called maximal cage connected partition if each and every G of Vi, the graph induced on Vi. So from now on, because any maximal cage connected subgraph is a induced subgraph, I'll just use the induced notation for this is what I mean by graph induced on Vi, and each G of Vi is maximal cage connected subgraph, and that means the lambda of the graph that is induced on this set is at least K, and that is true for each and every partition. And note that we say that this is a small technicality. It's just every vertex is trivially cage connected. So a vertex that is a singleton vertex is a graph by itself, and it is trivially cage connected because we can't remove any K edges from it to make it disconnected. And so that's the problem. And
it's like that's like a definition, right? I mean, how do you define? I guess the min cut of the vertex is 0, but your definition is to make the graph into two discrete parts. So
yeah, we can't make. Yeah, it's a matter of convention. We can't make it into two parts, so it's still, we say that it is cage connected because there are not even cages to disconnect as well, and like we can't make it into two parts also.
So we're talking about whether this partition is unique or not, like things like that.
Yeah, actually, this partition is unique. One reason is, let us say there are, it's not unique, then we'll have two sets which have intersection, and because a union of two cage connected subgraphs is actually going to give a cage connected graph as well. So it is not, it contradicts the maximality condition, because if A is MKS and B is MKS, then A union B is MKS, then A and B cannot be MKS, because there is a union B supergraph which is MKS, that is contradicting that A is MKS.
Why couldn't there be an A prime and a B prime that cut across them? I mean, why couldn't I have two subsets that are like this that are maximal, or two sets that are like this that are maximal?
Yeah, but
and they all intersect these intersect both of these.
Yeah, it can happen, but then assume that these are maximal cage connected subgraphs, and the union of them will again become cage connected, because if any union of two non-overlap intersection of two sets, two cage connected graphs will again become a cage connected graph.
Yeah.
So any of that that contradicts the initial assumption that A is maximal or A prime is maximal, or even P prime, any of them is maximal, it contradicts. Yeah. So that is so it exists, and it is unique as well. So the problem is basically to find it. And so there is a folklore algorithm which okay.
So can you get a sketch how do you prove uniqueness? Suppose you have two different partitions.
Yeah.
You know, a number of pieces that are both maximally K connected. How do you get a contradiction?
So assume that for a vertex belongs to set A in one maximal connected partition, and it belongs to B in another maximal connected partition. Both of A and B are different. And so A and B are two different sets which have a vertex containing, so they have non-empty intersection. And now A is cage connected and B is cage connected according to the definition of maximal cage connected partition. And so A union B will become maximal cage connected partition as well. Yeah. So actually,
I think there's like just go to more. Once again.
More, okay.
Yeah. I think there's this 5.
Hide floating medium. Okay, got it. So now this is the folklore algorithm for finding this partition, and we call it recursive mincut, whose name will be clear because of the algorithm. And we use Kager's O tilde M mincut algorithm. So there exists a O tilde M running time mincut algorithm given by Kager in weighted graphs. So given a graph, so what we have to do, we have to find the partition. So if it is cage connected, we are done. We'll just return the whole set as a cage connected partition. But if it is not cage connected, then we'll have a cut that is less than K, and we divide it at this cut. And recursively, we keep we check if this is cage connected and this is cage connected. If any of them is not cage connected, we keep running this recursively cutting along less than K cuts. And note that we are using global mincut algorithm, and so what the cut we get is actually mincut, but all we really care is just any cut less than K, because any cut less than K will not separate any cage connected component. So we don't want to cut cage connected component at any point of time, and that is why any less than K cut will actually give us what we need. But here we are using mincut algorithm. So we keep cutting, and at some point we start finding pieces that are cage connected, so we don't recurse on them anymore, and we keep doing this. And once we find all these chunks of the graph are cage connected, then we got our partition, and that is the maximal cage connected partition. And first thing, the correctness. So every partition is cage connected. That is based on our bottom out condition of the recursion. So so everything is cage connected, and assume that this is not maximal. For example, and then there exists a super graph which is actually maximum, which is actually cage connected. But at some point we have cut that superset using a cut of size less than k, because all the cuts that we are using is of size less than k. All these red cuts that we are using are of size less than k. So if there is a super graph that is cage connected, we would have cut it using a cut of less than k, which is not possible. And that is why this is indeed correct. Everything is cage connected and as well as maximal. And hence we found our maximal cage connected partition. This is the recursive min cut algorithm. And now we will see the running time.
So even if you have two min cuts, eventually you converge to the same.
Yeah, exactly. So now we see the running time. We have m edges in this graph. So the first min cut algorithm takes O tilde m, and then now we have parts of the graph, but there are m1 edges in this and m2 edges in this. So the total number of edges is actually m, and is actually less than or equal to m. And so on this part it takes O tilde m1 time, and this part it takes O tilde m2 time, but overall it is less than or equal to O tilde m time. So at each and every recursion level, we only take O tilde m time, and so it is just a recursion depth into O tilde m, the running time. And the recursion depth can actually be omega of n, because each and every time the recursion depth of this tree can actually be very skewed, and it's not balanced, then we can actually end up getting this omega n recursion depth. So in that instance, so the worst case running time of this algorithm is O tilde mn. So let's go into the previous work. So we have this problem is actually pretty classical problem and is studied from almost 1970s. The first algorithm given by Tarzan on weighted graph, on unweighted graph with biconnected component algorithm, which uses depth first search. It runs in order of m time, and so biconnected component is nothing but in unweighted with k equal to 2. And next in 2017, Sheshik et al. In weighted graphs gave an algorithm for parameter k, which is any k. The k here is the cage connected partition. So we have to give k for the problem to actually find the cage connected partition. And so for any k, the running time is O tilde mn k power order of k. Note that the k can be very large, because the weights of the graph can be very large, and so it can actually be kb almost poly n. So in that regime, this running time is not polynomial anymore. It is very bad dependence on k. And in 2020, Forrester et al. Actually improved this dependence on k to mk plus n power 3 by 2 k cube. Again, the dependence on k is there here, so it is not a polynomial if k is actually, I mean, it is polynomial, but it is not small running time if k is in poly n. Then we have seen the recursive min cut algorithm, the folklore, which in weighted case actually finds cage connected partition for any k with O tilde mn running time. So there's no dependence on k here. So this is good for our case where k can be poly n and there's no dependence, so it's O tilde mn. And our work now actually finds the same maximal cage connected partition independent of k in O tilde mn power 0.8. So the improvement is mainly improving in this n power 0.2 factor. And this is actually a barrier, and now we have broken that barrier with our algorithm. So the formal result is there exists a randomized algorithm that finds the maximal cage connected partition of a weighted graph in O tilde mn power 0.8 with high probability. So that's the main result. Is there any doubts? Okay. So the main framework that the algorithm proceeds, it's actually the idea from Sheshik. So the recursion min depth, the runtime of the recursive min depth algorithm is O tilde m into recursion depth, and recursion depth can be omega of n. That is when each and every time the less than k min cut that we are cutting is actually cutting only order of 1 vertices. So we are actually ending up with the bigger graph on the other side, and we still have to find min cut on this graph, and this can actually this very imbalanced recursion tree can actually make the worst case running time. And so we'll actually attack this particular worst case recursion tree and try to get improvement over the recursion depth omega of n. And so how do we do it? So find these small cuts of small cardinality quicker. So what do I mean by this? So we have these small cuts, these order of one sized cuts of size less than k. These are small cuts of small size cuts. Size cuts I meant by less than k, and the set of small cardinality I meant by the size of the set itself. So it is small cuts of size of smaller cardinality. And if we were able to cut all these small chunks from the graph, then we can actually end up with this residual graph much quicker. So I'll actually define what is quicker. But once we have this residual graph, now if we apply global min cut algorithm, if it is k connected, then we are done. We are going to return this as part of the partition. But if it is not kh connected, we have a less than k cut, and that has to be balanced. Why? Because if it is not balanced, that is based on the parameter balanced parameter, which I will be defining later. But if it is not balanced, then the min cut, this is a min cut, which is global min cut, and we have a side that is very skewed. Then we'll actually find this that actually becomes a small size cut of small cardinality. So that is the key observation. So because we have removed all small cuts, now whatever the cut we get is actually balanced. If not, it contradicts that we have removed all the small cuts. So the global min cut that we apply is actually balanced. And once we get balanced min cut, then the progress or the recursion depth will be small, because we are making progress each and every time much quicker, because the balance is good here. So that's the main idea. And this implies smaller recursion depth. And we call these small size cuts of small cardinality as local cuts. And I'll formally define them now. Formally, a sigma k set is nothing but a set S, which is subset of V of graph G, if the number of vertices in the set S is less than sigma and the size of the cut is less than k. So that is just simple what I have told before, like formally defining what small size cuts of small cardinality. And now we need this notion of extreme set. So I'm defining it here for our algorithm. So a set S subset of V of graph G is called extreme set if for all T subset of S, the weight of the cut of delta of T, I use delta to denote the cut edges. So the weight of the cut delta of T is greater than weight of the delta of S. So we have this set S, which has some cut size. And if all of its subsets have more cut size than strictly more cut size than weight of cut size of S, then we call this extreme set. So in some sense, all subsets have very well connected to the graph than this particular set, and that is why it is extreme. And so there is a good equivalent understanding of this property called extreme set, which is this. Equivalently consider G contracted S bar. So we have this graph, and each and every this is the set S, and we have all the subsets of S have cut size larger. So S is actually unique min cut of G contracted S bar, because every cut in this is larger. So S becomes the unique min cut based on this definition of extreme set. And we define something called sigma k extreme set, which means it's both sigma k set as well as sigma k extreme set. This is just combining definitions of these two. So is there any doubt?
So the part below, what was the argument again? The S is unique.
Okay. Consider this. This is S. So we have this blue yellow line as S, the settled left side of the yellow line. So this is S, and we have some cut value for S in this G contracted S bar. So it is basically saying I have contracted the complement of S into this super meta vertex. And so this is actually, these are the edges that belong to the cut S, but contacted to this meta vertex. And so now any cut that is any other cut in this G contacted S bar is actually cut in the original graph, which is having size larger than the cut S itself. So every cut in this graph is actually bigger than this cut. So this is S is unique min cut in this graph G contacted S bar. We'll move on. So now, before I introduce the main algorithm, I'll actually just quickly go through the local subroutine. So this is the theorem for the local subroutine. Given a graph G, which is here, and a vertex X that is belonging to V, and parameters sigma and K, where sigma denotes the size of the set and K denotes the cut size of the set. What we do is the local K cut subroutine either finds a sigma K set in the graph that is some set that is small, that is of size only sigma, and having cut size at most K, less than K. So we find this cut, so we can basically separate this vertex from the rest of the graph by this just K cut, or we guarantee that there exists no sigma K extreme set. That is, this is not sigma K set, but sigma K extreme set. So sigma K set along with some extra property that K, this is a unique min cut in the contacted graph. So we say that no such sigma K extreme set exists. And that is the local, how that is what when we say local K cut. So we are removing this vertex from rest of the graph by K many vertices, K many edges removal. And this happens in O tilde sigma power 4 running time. So in this case, if actually sigma is very small, it's only sigma power 4. So this running time is very less when compared to actually poly running times when sigma is very small. And that is what before I mean by quicker. So you can actually find these things much quicker than spending poly running times. And that will actually help us gain the improvement in running time. So we don't want to spend O tilde running time to actually cut these small cuts. So we are now only spending O tilde sigma power 4 running time to actually find these small cuts. So this happens in O tilde sigma power 4 running time. And in this context, I would like to tell you some lower bounds for this problem. So we show that omega, so we have actually given this local K cut algorithm in sigma power 4 time, and we show that there is no better algorithm that polynomially performs better polynomially in the dependence of sigma with sigma square. So basically what we tell is omega of sigma square is the best algorithm that you can do. Like epsilon is any small constant. So it's basically you can't improve over order of sigma square polynomially better. There is a gap here. And this is actually assuming OMV conjecture, online matrix vector multiplication conjecture. And we also show that extreme set relaxation is crucial. So as we have seen before, we are only guaranteeing that no sigma K extreme set exists. We are not guaranteeing no sigma K set exists. So this extreme set relaxation is crucial because if not, the problem is W1 hard with respect to the parameter sigma. So we basically can't get any FPT algorithm with sigma if we remove this relaxation that the set that we are guaranteeing, the not availability of the set we are guaranteeing is on extreme. So these are the lower bounds in this context. And now
What is OMV conjecture?
OMV conjecture is basically online matrix vector multiplication conjecture. We have an n cross n matrix, and which is the matrix M. And now we are getting n column vectors v1 to vn. So we want to give the product M v1, the matrix vector product. And this happens in online fashion. So we get one vector, we have to give the product, and then we'll get the next vector. So definitely you can't combine all of them and do matrix multiplication. So each and everything is coming one by one. So the best you can do for this finding all the n matrix vector products is order of n cube, which is the trivial. And I mean, it's not the best. There is little improvement n cube by log square n in Soda 2007, but it's order of n cube by log square n. That's the best one can do. And the conjecture is that you can't do polynomially better than n cube. So you can't do n cube minus some epsilon, where epsilon is greater than 0. So that is the conjecture. Assuming that conjecture, we can actually prove this. So now let's see our main algorithm using this local K cut as black box, which is again going to the main framework of the algorithm, but I stated here for completeness. So we don't know, first we'll start with this graph. We have many vertices, but we don't know where to look for these sigma K sets. We want some small cut, small sets, but small local cuts, but we don't know where to look for them. So we start with looking them around every vertex. And we have the luxury of looking them around every vertex because our running time is just O tilde sigma power 4. It is very small. So we can actually run it around all the vertices. And so we start with the candidate vertex. I represent it using the set L. And we start it with as vertex V. And we search in this orange vertex X. We'll search for sigma K set around that. If we find, we are good, but we don't find it. We don't find it. So we'll remove it from X, we'll remove it from our candidate vertex and move on to the next vertex. And we keep searching for like this. And we haven't found any of sigma K sets around these vertices. And now we are searching around this vertex and we found it. We found the sigma K set. What is the definition? Less than sigma vertices here and less than K cut size. So we found it and the cut size is less than K. So we can cut it along this. And once we cut it, we are only cutting less than K cut. So we are not spoiling our partition. We are respecting our partition. And note that we have completed searching on these boundary vertices, red three boundary vertices, but I still added them to candidate vertices because true, before there are no sigma K sets around this, but now I have removed these edges. I have removed these edges from being incident on them. So in this new residual graph, a sigma K sets might pop up because I have removed some edges. So that is why we have to again search along these vertices, because the result that we got before is for this big graph, and now in this residual graph we might actually end up getting new sigma K sets. And so I'm searching around, I added them to my candidate set. So that is what here I mean by cut it. So I cut it and then update L. So I keep adding more vertices to L.
So sigma is like n to the 0.2.
Yeah, exactly. So, and I keep recursing only on the larger side. I ignore the small side. I keep recursing only on the repeating only on the larger side until the size of the large set is less than n over 2. So, and now we have found like many sigma K sets. Like we have found all these 5 sigma K sets. We have removed them. So now we end up with this residual graph, and we say we exhausted all the candidate vertices that we can search around. So now we are sure that there is no sigma K extreme sets in any of these. So every time we get only guarantee that no sigma K extreme sets exist. So there is no sigma K extreme sets in this graph, in the residual graph. Now if we apply min cut, the global min cut now, if it is greater than K, we are done, because it is K connected and we'll add it to our partition. But if it is less than K, then it has to be balanced. It has to be both sides, at least sigma many vertices has to be there. Because if there are no sigma vertices on one side, so that side will become sigma K extreme set, because the size is less than sigma and the cut size is less than K. And this is min cut, so it is unique min cut in the contracted graph. So this will become a sigma K extreme set, and that contradicts that there is no sigma K extreme set containing this vertex, any of these vertices. So that is why both sides it has to be greater than or equal to sigma. And again, because we used our global min cut, we cut, and one side it will be less than or equal to n over 2, and the other side it is greater than n over 2. So again, because we have to recurse on the larger side, and we actually add this cut the boundary vertices again to the candidate vertex, because now again small sigma K sets might pop up around them. And once we have completed them, we have exhausted all, and we keep doing it until every large side becomes less than or equal to n over 2. And now even this side actually became less than or equal to n over 2. So we now end up with some bunch of graphs which are each and everything is of size less than or equal to n over 2. These outer small vectors we got through local cuts. These bigger sets we got through global cut, but nevertheless we just found all of them as less than k cuts, using less than k cuts. And so we end up with this less than or equal to n over 2 graphs. Now all our target is to find the maximal k connected partition on the smaller graphs. We haven't certified that any of this is k edge connected yet. So we'll just recursively apply. So, but the size is reduced by half. So we have made progress. And so apply the same algorithm again, starting from this step on each part. Each and every part we go and apply this algorithm and recursively find the maximal k edge connected partitions. But the runtime only increases by just log n factor because we have made progress by constant factor in the size, reducing size of the input. And note that the recursion depth here is actually improved by n by sigma. Why is it? Because every time we apply this global min cut, we are reducing the size of the graph by sigma. So at least sigma many vectors are being removed from the graph. So we only need order of n over sigma many global min cuts algorithm to actually reduce the graph from size n to n over 2. So that is why the number of global min cuts we have reduced, and that is the saving. This by sigma is the saving that we are getting. So which is actually the improved recursion depth. We need not apply global min cuts n times. Now we are only applying it order of n over sigma times, and this is the improved recursion depth that we are getting. And because in the optimizing running time, we take sigma equal to n power 0.2, and that is why we actually get our algorithm runtime. So this is the actual improvement we are getting when we are using that local k cut subroutine. Is there any doubt?
What about the find to compute the local cuts?
The local cuts. So let's see how many local cuts we need to compute. So initially we start with all the vectors. So we have n many local cuts we have to compute. But each and every time we cut something, we are actually adding the boundary vectors. So how many more vectors we can add into the candidate set L is basically number of edges, because we remove an edge, we add a vertex. So once we, so number of edges, number of vectors that are added to this candidate vertex is basically number of edges in the graph. So we only use at most m many local cuts. So the total runtime that we get for local cuts is m sigma power 4, and for the global cuts it's m n by sigma, and that is why the total becomes balanced at sigma equal to n power 0.2. So that is our main algorithm, and now we'll see, we'll focus on our subroutine. So before we go to our subroutine, we'll just take a detour through Karga's min cut, and because it is important for our, it's the key idea in our local subroutine, and we'll see it from our perspective. So recall Karga's min cut. So the random contraction algorithm given by Karga. So this is different than the O tilde m min cut we are using. So this is the random contraction algorithm. Given a graph G, V, E, W, which is weighted, min cut is preserved with probability 2 by V square. So which means after B minus 1 random edge contractions, the graph that we get is actually min cut with probability this much. And that's the statement given by Karga. And he told that random edge contractions can actually be done by sampling a uniform edge. That can be done by using a random rank function by choosing the edge with minimum rank value. So this idea I'll just briefly explain here. For example, we have 3 edges E, F, G, and each and everything is of weight 1. So each and these 3 edges sample a random value between 0 and 1. So they sample a random 0 and 1 value, and now we see that probability of minimum of these 3 values is actually for it to be R of E, it's basically 1 over 3. because there is no reason to be biased against anything here. So this will all of them being equal to the minimum being equal to any one particular is basically 1/3. And so this is basically, so the same process can actually be extended to weighted graphs using inverse probability distributions. So now that we have R of E 3 edges, and we can sample them by just taking minimum of these 3 random rank values. We just use the word rank to be not confused with some weight function, another weight function W, which we have here. So these we call rank. So we just take minimum of them, and that is how we sample an edge uniformly. So now let's see how sampling with respect to R works. So we start with a edge. This is the minimum ranked edge. So we pick it, contract it, and then this is the minimum ranked edge. We pick it, contract it, and so on. We actually do, after B-1 edge contractions, we'll end up with these 2 meta vertex, and with probability 2 over V square, this is min cut, and that's the algorithm given by Kargar. Now let's see, now I unpack these meta vertices into the edges that are contracted. So all these edges together contracted to that meta vertex, and these together contracted to this meta vertex. So these are the edges. And what are these edges? Basically, these edges are nothing but the edges of the minimum spanning tree with respect to the random rank function. Because what is the process we did? So each and every time we are picking up the smallest rank value. So that is nothing but we are applying Kruskal's algorithm on this rank function on the edges. So we are applying the Kruskal's algorithm. So the edges that we get are nothing but the edges of the minimum spanning tree with respect to the rank function. And so basically what this gives us, this tells that with probability 2 over V square, both sides of a min cut are spanned by the minimum spanning tree computed with respect to a random rank function. And this is the key idea. So the randomness or the probability is coming from the rank function. So we are actually randomly choosing a rank function on all the edges basically, and that rank function, if we find the minimum spanning tree, that is actually respecting the min cut. Is this idea clear? So now what if we have an rank function, then if MST with respect to our spans both sides of the min cut. So whatever I told before, so if we have a rank function that is actually spanning the MST of that rank function is actually spanning both sides of the min cut, then we do the following. So note that this is the final edge that we haven't contracted in our Kargar's random contraction, and we know that the rank of this final edge is greater than all the other edges. That is why we haven't contracted. So now let us see, putting this in mind, let us apply Prim's algorithm, which again gives us a minimum spanning tree, with starting from some vertex X. So what do? We expand this X along the minimum ranked edges along its cut. We keep doing that. So along the cut edges, we keep expanding the minimum ranked edges. And at some point we encounter this final edge, this green edge, which I colored here red. And we encounter this, but we don't contract along this, or we don't expand our Prim's set along this, because the rank of this particular edge is greater than all the other edges. So we don't expand along it, and we keep spanning one side of the min cut before actually proceeding to expand along this red edge. We don't expand along this red edge, and we span all one side of the min cut. And at this point, the set that we arrived at is actually the min cut set. So if we at every point, if we actually maintain this purple cut size, so we keep maintaining this purple cut size, and at this point we again store this purple cut size. So if we complete this Prim's algorithm completely, we definitely, out of those n many expansions of the Prim's, one cut will be actually minimum cut. So we actually found our minimum cut by applying Prim's algorithm, if at all we have a good rank function that spans both sides of the min cut. And that is what he's here, like starting prim with respect to this rank function from any vertex spans min cut before crossing it. So that is why we can find that particular cut size if we plan to maintain it, and that is how we find min cut. So, and this, as we seen before, this happens with only probability 2 or v square. Although we assumed that such a good rank function exists, but this happens with probability 2 by v square. So if at all, this is a just different way of viewing the Kargar's min cut algorithm. To improve the probability, we just repeat it order of v square many times. And so now that we have seen Kargar's algorithm in a different way, we'll see how to apply this idea in a local setting. And that is what will give us local subroutine. So just to recall, sigma k extreme set is a set which satisfies 3 conditions. One is S less than sigma, so size of the set is small, cut size is small, and its unique min cut in G contracted S bar. That's the definition we have seen before. And assume there exists a sigma k extreme set S containing X. So this is set S, which is sigma k extreme set, and it contains X. So that is number of edges are small and number of edges are small. So consider this G contracted S bar. In this G contracted S bar, S is unique min cut. So this yellow cut is basically unique min cut. And so we start from this set X. Okay, we start and we now maintain this small value, maintain the cut value of this purple set as we keep growing. So we return if the cut size of that set we are maintaining is actually less than k. Then we will actually find the sigma k set that we have told in the local k cut subroutine. But if not, we'll keep expanding along the rank edges, minimum rank edges, and at every instance, at every expansion or contraction of the edge, whatever we can think of it as, we'll calculate the cut size, and we'll store it, like we'll basically store the minimum one, and if at all it is less than k, we'll return it. So we keep repeating this step, and we are expanding our we are expanding our set X, the purple set, by using Prim's algorithm on the rank function, and we are maintaining this set. And after, if the size of the set X is greater than or equal to sigma, then we just output some null, because the size budget or the constraint size is sigma, and we shouldn't cross it. So we'll just return null and see that we are expanding, and at every point we are expanding the set, and if some place we'll find the set less than k, we'll return it. So this is the local prim algorithm. This small subroutine which we are running around a particular vertex X is local prim algorithm. And now we'll see why will it have to return such a set? Why can't it just keep doing and never be able to return such a set? So assume, because we have this assumption that there exists a sigma k extreme set where S is unique min cut in this G contracted S bar. So we keep expanding S, and because S is unique min cut, it can't cross this cut S before it actually spans this particular all vertices on one side of the graph. If you are considering this G contracted S bar, it can't span the cut S before actually spanning this. So the prim algorithm have to actually contract all the vertices on one side to span to cross this. So at which point the cut size of this particular set is less than k, so we won't even cross it. We'll just return this set, because we, in our previous algorithm, we have actually found a cut of size less than k, so we'll just return it. We'll never cross it. We never need the chance to cross it actually, and that is why local prim returns S. And this is basically where we apply the previous statement with probability 2 by v of G contracted S bar square. We get such a good rank function, and so we can start prim with respect to that rank function, and it spans the min cut, which in this case is S before crossing it. So that is why we find the set S.
Actually, then why is it guaranteed weaker? Because you said like it might return some non-extreme.
It might return some non-extreme set if we actually found it before.
If there exists the sigma k extreme set, then there's no smaller set.
It can be actually.
Yes, yeah, I mean, yeah.
So it's sigma k extreme set doesn't mean this has to be k. So it can be like k by 2. And there can be another set that is 3k by 4 inside it.
Okay.
And if luckily our algorithm able to span it, then we'll just return it at 3k or 4. We don't want extremeness condition in our thing, so we'll just return at this at the previous point itself.
So yeah. So if the cut size is k, then it's gonna return this. If
Cut size is less than k.
Yeah, so if s is exactly k minus 1 edges, then actually you're gonna find that exact size.
Yeah. If I see, yeah, exactly, because then there won't be any other thing that is smaller than k. Yeah. So local prim will either return some sigma k set, or will definitely return this sigma k extreme set that we are assuming to exist.
So you don't even like you don't even open the black box part of that one. All you need is like that.
Yeah, we only need this one. Yeah. So now what we have seen, just to summarize, if there exists a sigma k extreme set containing x, that is the structure that we have seen before. If there is such a good set around x, then the local prim using random rank function finds the any sigma k set or the sigma k extreme set. For now, we'll just say sigma k set, and because sigma k extreme is also a sigma k set, and that happens with probability 2 by sigma square, and we just repeat it order of sigma square log n times to improve the probability, and we achieve it with high probability. So basically, this local prim algorithm is returning if sigma k set, if we assume that such a thing exists. So the local k cut algorithm is nothing but order of sigma square log n times the local prim algorithm, and we use some bookkeeping to actually run the local prim algorithm in O tilde sigma square times, because the volume of the set can be much larger, because it involves the cut size of X, S as well, and the volume of the set can be much larger. But all we do some bookkeeping and pre-processing, and we can actually make local prim run in O tilde sigma square times. So we get the O tilde sigma power 4 running time that we claim in the local subroutine. And note that we are assuming sigma k extreme set. So just flipping the things, if we don't assume it, we either return this or guarantee that no such thing exists with high probability. So this is the main local k cut statement that we assume, the subroutine that we assume. Is there any doubt?
So I guess like the local prim algorithm will be the most complicated part of the paper, I guess.
Yeah. Actually, there's only no notation, but the idea is pretty simple. It's just trying to make how to make it work for a weighted graph with, and actually most of the probability calculations we put it in appendix, but it's just making things work to weighted graphs. So the open questions is, we have seen a local k cut problem. We have seen an O tilde sigma power 4 algorithm, and we already saw that this is just being sloppy here, minus epsilon I removed. Assuming OMB, omega tilde sigma square lower bound we have, and so we have to, if we have to close this gap. That is one open question. So if we close this gap, then the exponent actually reduces, because instead of sigma power 4 we get sigma square, and then that gives better algorithm. And the next obvious open question is, we have maximal case connected subgraph partition. This is folklore and this is our algorithm, but why it has to be 0.8, right? So why can't it be O tilde m, or is there some good midpoint where we struck and we can find upper and lower bounds? And that is some interesting open question to work on. And note that if you actually find a better algorithm for sigma of local k cut, it will only lead us to O tilde mn power 0.67, because sigma square will lead us to this exponent, and that is not even so. This approach alone will not just give us improvement. So we either have to push this approach and arrive here. That is one good thing, or we want to push beyond this approach to actually arrive at O tilde n. Thank you.